All right, guys. First lecture in chapter 8, mixtures and solutions. Chapter 8 is the last chapter that will be on your test in a couple weeks. So this will be it. It's a lot, but chapter 4, 5, 6, 7, 8 is a lot, but we believe in you guys. So we're going to talk about mixtures and solutions. We're going to start with a chat on pure substances versus mixtures. Now, traditional chemistry classes actually start with this and dimensional analysis, like converting between units. So what do we need to know about pure substances? So somebody shout out a color. I heard yellow first. All right. So pure substances and mixtures. Pure substances are comprised of only one type of substance. Now, it doesn't have to be an element, but it could be. It just has to be one type of substance. So, for example, examples of pure substances would be like neon, like a neon light. So that's an example of an element that is a pure substance. But also, oxygen gas, 2 oxygen atoms bonded together, if that's all there are in your sample, it's a pure sample. Sodium chloride would be a pure substance. 2 different types of elements, but if they're bonded together in that same ratio, and only in that ratio, it's a pure substance. Carbon dioxide would be a pure substance. These are things just by themselves bonded together. And a good way to look at this is if you draw the representative particle, only that type exists. Right, so we did a lot of work drawing representative particles. So in a pure substance, only that type of representative particle exists. So mixtures, as you might be able to guess, comprised of 2 or more substances. So what might be some examples of mixtures? Just shout them out. Kool-Aid. Kool-Aid. What else? Milk. We're going to talk specifically about milk in a little bit. Close. Cake batter. Tap water. I just wrote cake water. Cake batter. Tap water. You could make a lot of money if you made cake, like water that tasted like cake. Oh, it might be gross, but it might be awesome. Might be awesome. Okay, so here you'd have multiple types of representative particle. I don't know, maybe cake water would be good. I had cake batter ice cream this weekend and it was awesome. All right, so we've talked a lot about pure substances already throughout the year. Now we're going to talk about mixtures. We ready to move on? Wait another second. All right. So homogeneous versus heterogeneous mixtures. Oops. All right, pick another color. Green. I heard green first. All right. So a homogeneous mixture. Let's use our SAT skills. If I see that as my root or my prefix, what does it mean? Same and different. So in a homogeneous mixture, the compounds or substances, because they don't have to be compounds necessarily, are uniformly distributed. which basically is the same. It's the same throughout. So anywhere you look, test, sample that solution, you should get the same properties everywhere. So a homogeneous mixture has to be the same phase throughout. That means you can't have like solid and liquid, a homogeneous mixture that's both a solid and a liquid. It has to be either all solid, all liquid, or all gas. They can't be separated by simple means. Means like you can't just sift it out like you're panning for gold or something. So homogeneous mixtures, it's difficult to separate them. And lastly, most are what we call solutions. So the vast majority of homogeneous mixtures we're going to talk about are going to be solutions. Okay, so if homogeneous mixtures are evenly distributed, what do we think about heterogeneous mixtures? Not evenly distributed. These are not uniform. Which means they're not even throughout. Also, different samples of the same mixture are different. So that means you'd have different composition, could have different physical properties. And they can be separated easily. Most of them can be separated easily. Now, because we're going to leave heterogeneous mixtures behind for now and focus on the homogeneous mixtures, what would some examples of a heterogeneous mixture be? Salad dressing. Right, if you took, that's why you have to shake up the bottle. Salad dressing is great because it gets to this not uniform. So you have to shake up the bottle of salad dressing to get it to be pretty evenly distributed. But if you sample different areas, you'd get different amounts of vinegar and oil. Yeah, Edward, and then with Ben. Like what? Like a rock? Like the rock? Sand. Yeah, sand. I also like sand and water as an example. Right, because if you just put sand and water and shake it up, you'll have a heterogeneous mixture. If you sample different areas of it, you'll get different amounts of sand. Yeah. So the question was coffee with stuff in it. Yeah, so like coffee with, well, coffee, iced coffee, for sure. Like tea with the tea leaves in it would be another good example. Yeah, I know a lot of people drink their tea with like the leaves in it. I know my family does. Yeah. So the question was homogeneous versus homogeneous. I don't know that there's a difference between that. Because we call it homogenized milk, right? We don't call it homogenized milk. Right. Right. Mm-hmm. I'll be honest, I don't know if there's a difference between homogeneous and homogeneous. We'll just call it homogeneous, but if you say homogeneous, meh. Either one's fine. Yeah, I think they probably mean the same thing. It's just different. No, it's the same spelling. It's sort of like we had the discussion about trigonal versus trigonal and pyramidal versus pyramidal. All right. So, things you should know. 8.1. This is a long definition. When one substance, called a solute, dissolves into another substance called a solvent, the resulting mixture is called a solution. So that's just a little vocab. What you need to know about the solutions is they have the same properties and composition throughout. Remember, we talked about that with homogeneous mixtures, that they have the same properties throughout. In a solution, the molecules or ions have completely separated from one another. So in salt water, I'll give you a little hint. Sneak preview, salt water is a solution. The Na and Cl's ions have completely separated from one another, right? They're no longer stuck together as NaCl, Na ions and Cl ions. So no particles in the solution are large enough to scatter visible light. So they may absorb light, and that's what you guys did in the lab with the blue food coloring. It absorbed visible light, didn't allow it to transmit through. Many things will absorb visible light, but it doesn't scatter. What does it mean to scatter light? I couldn't hear. Yeah, so this would be an example. So if I have a solution and I shadow color, blue, I don't even know what cyan is. If blue light was shown onto it, scattering would be it hitting something in here and then bouncing off in different directions, right? This is scattering. So solutions do not scatter. So if I took a laser beam and pointed it through a solution, it should come out exactly the same on the other side. The glass, depending on what it's in, the glass of the container might have something to do with it. But in general, it should go straight through unimpeded. If there was stuff in it, it would scatter. So components of a solution cannot be separated by filtration, which is what we commonly think of to separate stuff, but can be separated by chromatography or distillation. And we'll do a chromatography experiment probably the week of the test, so like after the test. All right, so this is what basic solutions is. Now, parts of a solution. The solute is the one that is dissolved. So you can almost think of the solute, if you're a grammar person, like this is the passive. The solute is the passive. It's the one getting the thing done to it, even though it has to do something too. But the solvent is the one that does the dissolving. You can say, oh, that's great, Mr. Bennett, but how do we know which one is which? How do we know which one is being dissolved and which one does the dissolving? Here, I'll write pass. I don't want to. No. If the two substances are normally different states of matter, the liquid or gas is the solvent. So, for example, we talked about salt water briefly. Salt and water are different phases. So, what's the solvent? The water. The liquid phase. Yeah. No. You can have a gas dissolved in a liquid. And in that case, then the liquid would tend to be the solvent. Yep. Can you have a liquid dissolve? You can have, so there are some exceptions to this, because you can have a gas dissolved in a solid, which is how one of the ways they do hydrogen fuel cells is they actually dissolve the hydrogen gas into platinum. And then that's how you can store it, which is pretty neat. But this is just a general thing. We're not going to be talking about things like that. If the two substances are in the same phase, here's the way you can generally think about it. The one that there is more of is the solvent. Most of the time it'll be pretty obvious, right? Again, with salt water, you have a lot more water than you have salt. So the water is the solvent, even if you don't use this idea of different states of matter. Yeah, in previous years, we've had this big whole, like, what's an example of a solid in a solid solution? Because you can have that, a liquid in a solid. Your fillings are what's called an amalgam, where they put mercury, and mercury gets dissolved in whatever the rest of the stuff is. I think it's silver, and that's a solution of a liquid in a solid. But we're not going to talk about it. So let's do examples of solutions. So I gave you salt water. Let's see if we can get at least like 10. What's that? Yeah, but that's similar to salt water, right? In that you have all right. Gold in, it is aqua regia. It's a mix of like nitric and sulfuric, right? All right, let's do some maybe more common ones that we all know. Kool-Aid, as long as you don't over sugarify it and leave some at the bottom. There was an oh yeah from the back. Food coloring and water, that's the one you guys studied. Let me give you guys a hint. Air. Air is a solution. All these gases mixed together. So they're also, I mean, if you want to argue, like, nitrogen would be the solvent, but we tend to not think about it that way. Right. All the other things, yep. Yeah, Wesley. Interesting question. Would plastic be considered a solution? Plastic gets into this idea of polymerization, so it's a little bit different, but that's good thinking. Good thinking. So acids would be, yep. Acids and bases. 1, 2, 3, 4, 5, 6. All right, come on, 4 more. Yeah. No, that's good. When you whisk an egg, is that considered a solution? No. Think about it this way. Can you shine a laser beam through the mixed thing without it changing the laser beam? Well, you don't do that in your kitchen? No, so we'll talk about what that probably is in a couple slides. I'm not 100% sure, but I think it's actually probably a heterogeneous mixture because you probably have chunks of like yolk, and unless you perfectly get it, and then it would be what we're going to talk about in a minute. Brass. So brass is a solid solution. There's one that I'm really glad nobody came up with. Bronze. Yeah, brass and bronze, same idea. Good thinking. Well, steel, same idea. Yeah. What's one that I'd be really glad you guys didn't come up with? Booze. Wine and alcohol, like wine and spirits are solutions of ethanol and water with some other stuff. Beer, on the other hand, is not, because beer has like stuff in it that keeps it from being a solution. But wine tends to be, and so does liquor. Yeah, vodka looks very similar to water, I've been told. Yep. I will say I went to visit Moscow a number of years ago, and yeah, there was a lot of vodka all over the place. Yeah, it was interesting. Okay, so we'll leave it at 8. 8's fine. You guys got the big ones. So basically, we're going to be looking mostly at things dissolved in water. That's the majority of ones we're interested in. Us involve stuff in water. For us, involve. Yeah, that is really ugly. Let's see how neatly I can write involve. Wow. So I guess I can have good penmanship if I take the time. Yet, I don't know. All right. So there are other types of mixtures that are not solutions that might seem like solutions. So one of these is called a suspension, which is exactly what it sounds like. So this is a heterogeneous mixture. That contains generally solid particles suspended in a fluid. Whoops, sorry. So you can think of this as like dirt in water. So if I have a sample of dirt and water and I shake it up, the dirt particles will distribute all throughout the water, right? If I let it sit for an extended period of time, what's eventually going to happen? The dirt will separate, the dirt will settle. So suspensions eventually settle out. So essentially what they do is they self-separate if given enough time. There are some suspensions that will last for a very, very long time, but others that will go away quickly. But in order for it to be a suspension, it has to be a heterogeneous mixture containing solid particles that will settle out. Now we get to the tricky one, which is colloids. Colloids are a homogeneous mixture with suspended particles. Now, colloids, these will actually, the real difference between colloids and solutions has to do with particle size and the fact that colloids will diffract light. The suspended particles are large enough that light will bounce off them. If you look to your right, you'll see the example of the most famous colloid. Not on the right-hand side. Not the person to the right of you, but on the right-hand side slide. The next slide, you can see. Yes? No. So the question was about non-Newtonian fluids, which maybe we'll do at the end of the year for fun. But it's not, non-Newtonian fluids are not on the AP. They are very fun. All right. And then aerosols. These are solid or liquid particles suspended in air. All right. So aerosols, when you think of aerosols, what do you guys think of when you think of aerosols? Hairspray, bug spray, Febreze. What's that? Global warming. Thank you. That was one of the ones I was really looking for. So aerosols, pollution is an aerosol. Right? You have these solid particles or liquid particles suspended in the air. I was really, really considering spending next year in China with my family. Like really, like I had it all planned out, all set up. I'd already talked about it with my boss here. I was going to do a year sabbatical. And then I started looking into the cities, and like you walk around, it's almost like it's snowing. The pollution is so bad in some of the cities. Yeah, so the quote was, you can hold someone's hand that you like, but you can't see their face in some of the cities. Or walking your dog, you can feel the leash, you can't see the dog walking. So, yeah, pollution. Also, another one is like, do you guys take your asthma meds? Some people, if you have asthma, which is one of the things that being in a polluted environment can give you, if you take your asthma meds, those are considered aerosols. So my first job out of college was technically developing aerosols because we were making solid particles that would be suspended in air that you would breathe in, right? So they were aerosol particles. We're not going to talk a huge amount about these. I'm going to give you one more slide on colloids, but these are things that you should know about. All right. So a colloid, it's a substance dispersed evenly and microscopically throughout another substance. But, oops, wow, that was ugly. But solute, no, it's not solute. Dispersed substance remains stuck together a bit. So in the example of milk, and I'm sorry if you guys don't know this already because it's really disgusting what milk actually is, but you should drink it because it's good for you. Milk is particles of fat. That's what that white stuff is that makes milk milk. That are insoluble in water and suspended. We'll say insoluble and suspended in water. And diffracts light, right? You can't shoot a laser beam through milk without the light getting scattered. Or sorry, I shouldn't say diffract, should say scattered. Scatters light. So, Gigi, was it you I was talking to about dynamic light scattering? Who was I talking to about dynamic light scattering? I remember talking about it with one of my students. So that's a way you can measure the size of these particles by shooting a laser at it and see how it diffracts. Well, oh yeah. Oh, sorry, egg yolk. No, but this is a side conversation that I had with someone. I forget. Yeah, egg yolk. Egg yolk. You might get this if you really homogenize the heck out of it, but I think you'd be left with a heterogeneous solution. What about almond milk? I'm not sure what almond milk is. That's a good question. I mean, it's certainly not a solution. It might be a colloid. Let me look into it because we drink a lot of that at home. Fake milk that doesn't go bad. They have powdered milk, which is just like it's powder. Oh, stuff about acid. The question was about milk that doesn't go bad. I don't know what that would be. It probably wouldn't be milk. It would have to be some sort of milk analog. Yeah. Yeah, you're using the term milk very, very loosely at that point. But yeah, you can evaporate the water off, and then you're left with solid stuff. And maybe that's how they do it. I don't know. I don't know. I drink almond milk. I drink normal milk. So really what this is based on is particle size. So if the particle, there's some ambiguity between colloids and solutions on the low end. So if your particles are of a certain size, they're big enough to be considered a colloid. If they're smaller than that, it's a solution. But really, what I want you guys to take away from this is particles that are suspended and diffract light, but they're not fully dissociated. They're not a full solution. Yeah. Good question. The colloid can be centrifuged in most cases, whereas a solution could not be centrifuged. Although I wonder if you centrifuge a solution, if you wouldn't get some level of difference. But I don't know. I actually don't know the answer. But that is a good way. You can certainly centrifuge milk and get separate into the two phases. Yep, good. Okay. So where are we going to go next? Solubility. How do we know if stuff's going to dissolve other stuff? So in order for one substance to dissolve in another, the intermolecular forces between them must be compatible. And substance with incompatible intermolecular forces, polar solvent like water, nonpolar substance solute like vegetable oil, will not form solutions. They may form a suspension, but if it can be broken into chunks, and if the solute can be broken into small enough chunks, they'll be a colloid, right? So you can have a colloid with incompatible intermolecular forces, like we're talking about milk with fat and water. But in order to make a solution, they have to dissolve fully in one another and have compatible intermolecular forces. So what's our general rule for making one substance soluble in another? You've heard this. It's so same like dissolves like. So general rule is like dissolves like. So compatible, we said that word compatible intermolecular forces. They don't have to be the same, but really what they break down into is charged versus uncharged. So charged are ionic or polar, and uncharged is nonpolar. So in order for things to be like, it can be ionic and polar. We don't really talk about ionic solution or ionic liquids, right? So generally this would be something ionic dissolved into a polar liquid. For uncharged, it would be nonpolar and nonpolar. So the question is, what about slightly polar mixed with nonpolar? You get, this is our general rule of thumb. There is ambiguity even there. So how do fish breathe? Through gills. But what do they breathe? They breathe oxygen, right? Is oxygen polar or nonpolar? Nonpolar. It has to be nonpolar. It's just O2. Is water polar or nonpolar? Polar. Where do the fish get the oxygen from? If oxygen is not the same as water. Do they break apart water molecules and leave behind hydrogen? Is it magic? They have a full octet and that's especially stable? So really what happens is, even though this is our general rule, there is some level of, you can have oxygen dissolve in water to a very little degree, right? A very small amount of oxygen can dissolve in water. And so when fish have water pass through their gills, they filter out that oxygen and that's what they breathe. It's not a huge amount, but it's enough for them to breathe, the amount of oxygen dissolved. So this is a general rule, but it's not perfect. It'll be good enough for what we're going to do in class. Okay. So intermolecular forces in salt water. Here's where we get to watch some demos. Or not demos, but simulations. So I'm going to ask you guys at home to bear with me, well, and in class to bear with me. We are going to use Odyssey, which is a simulation software, and it's a little unwieldy at times. So I'm just going to grab the mouse. All right. So what this allows us to do is it allows us to take a look at things up close on the molecular level. So, very good. Now, if I want to do, so this is an example of air, and if I hit play, you can see the air particles move around, right? What do you guys think these blue ones are? Nitrogen, how'd you know? Yeah, there's a lot more of them than anything else. How about the red? Oxygen, right? So, let's do seawater. Whoa, right? Whoa. So, we have water molecules, and embedded in there somewhere is sodium and chlorine. I'm going to turn the lights off. All right. Now, to make it easier for us to see, I'm going to select all the waters, select all, actually, wait, sorry. Select group, view, style, let's do ball and wire. There we go. Okay, so now you can see inside here I just have a sample of, and it's actually not balanced because I have 1, 2, 3, 4 of one type of ion, and 1, 2, 3, 4, 5. Oh no, there's a fifth one, so it is balanced, 5 and 5. Which ion, if this is NaCl, there's 6. That's okay. Which ion is the sodium? You guys, one of the things you should be able to do, and this actually came up on the AP test last year. Why do you think? Okay, so the question was sodium, so sodium is green because it has a greater atomic radius, but we're not worried about atomic radius because at this point they're both ions. So what happens to sodium when it becomes an ion? It shrinks a lot. It loses its whole outer shell. So which one is sodium? Blue. Perfect. Okay, so let's zoom in and let's see what's actually happening here. Let me zoom in. Okay. All right. So if I hit play, we can sort of watch how the water molecules are interacting with the chlorine. And if I zoom in more, what part of the water molecules are surrounding the chlorines? The hydrogens, right? See all these white close to the green? Now, why is that? Well, chlorine is negatively charged. The hydrogen is partially positively charged. So Coulomb's law, or opposites attract. The hydrogen part of water is going to be attracted to the negative chlorine. And if I zoom out and I look at sodium and I hit play, you can sort of watch what's happening. Now see here, the oxygens are the ones that are surrounding the ion. So this is actually what's happening in water. When you dissolve sodium chloride in water, the water molecules are sort of not really lining up perfectly, but sort of forming around it with opposite charges attracting. So if I go back to my PowerPoint and we do this, the ions split apart. Shout out a color. I heard red first. Cl minus, Na plus, and then I'm going to use blue for water. So, sorry, what was the question? Oh, whoops. Dope. Thanks. Now, also remember that things are moving around all the time. So we're going to look at it as if it's not moving, but so H, O, H, partially plus, partially negative, partially plus, H, O, H, partially negative, partially plus, H, O, H, partially plus, partially negative. Now, it's not going to line up with like both H's all like locked in around the Cl minus. There's some movement around. It's just as it's moving, this part, the H part of the water molecule is going to be attracted to the Cl, whereas here it's going to be the O. Now, what we're going to find out as we move ahead, like later, one of our last chapters, is going to talk about solubility. Not all ionic compounds are soluble in water. But for now, we're just going to do this like dissolves like idea. So ions are charged. Water has permanent partial charges. Therefore, they dissolve. All right. Does anybody need me to wait? Okay, so we'll keep that. Keep. And we'll go back here. Ethanol and water. So now, this is the one that I'm glad that you guys didn't get earlier. Ethanol is basically what's in things like vodka and wine and such. So now let's look here. Here's our ethanol molecule. Ethanol is C2H5OH. So you can see the big black blobs are the carbon, the red blob is the oxygen, and the white is the whites are hydrogen. So let's see. Let's pick one right here. No. All right. So if I zoom in, I can see I have that polar area. Whoop, lost it. Whoop. Oh. All right, there we go. Oh, too much. All right, here's what we're going to do. We're just going to look at one. They're too close together. Okay, that one. And we'll just zoom in. Zoom in. All right. So what part of the water is pointing towards the oxygen? The hydrogen. See, you guys can see the water molecule here. The white part is right next to the oxygen. The white part here is right next to the oxygen. And then what do we notice about this water molecule here? What part is pointing towards the hydrogen? The oxygen, right? So you can see how they're sort of lining up around that area. Now, if we watched randomly throughout, there wouldn't be much of a pattern that we could denote from looking at the rest of the molecule. We can only really look at that alcohol functional group to determine how the molecules line up. So what does that look like if we're drawing particulate representations? Okay. So I'm not going to worry about it being rubbing alcohol. I talked a little bit earlier, I think, when I was actually doing the review about if we do, whoops. Ink color, pink, I heard pink first. All right. So if I just do the R equals organic chain. So in this case, we don't really care that it's rubbing alcohol or ethanol or methanol. So we'll have a couple of these. I'm still drawing it bent around the oxygen. So we know that this is, go back to my pink. This is going to be partially negative. This is going to be partially positive. Partially negative, partially positive. And then blue for water. So we saw that the hydrogens were lining up around the oxygens, and the oxygens from water were attracted to the hydrogens. Now, what's so special about the interactions that are here? What's interesting about the interactions between water and any alcohol? So the alcohols are soluble until we get really long chain alcohols. There's something special about what can be thought of as the interactions between these molecules. I heard it. Yeah, so we can get hydrogen bonds between these molecules. Now, that's not true of everything that dissolves in water. It just happens to be true in this case for rubbing alcohol. All right. This is a good place to stop for the day, especially because you guys had a quiz. So